Hey, we're on page 838, which is why you clicked on this video. We're going to continue our conversation on two-way relative frequency contingency tables. That's a lot of vocabulary. Two-way, because two category. Relative frequency, because eventually we want percentages. Relative is like out of the total. And contingency table is actually redundant because I already said two-way. But contingency is about how we're trying to plan for every outcome. So we're planning for all the different categories that are available and their results. I'm using page 835 with that information to answer part C. What is the probability that the person is left-handed, participating in individual sports, so there's an implied and intersection there, or right-handed, participating in team sports, so another implied intersection. Again, this is compound probability, so multiple things can be calculated all at one time. The nice thing is, if we have the frequency table, the two-way qualitative data frequency table, then left-handed and individual is an intersection, and that shows up right there. And then right-handed and team is also an intersection, shows up right there. And there's no overlap between those two choices, so we have nothing to subtract. 3 out of 63 people are left-handed and play on individual sports, in, on, around. And then 23 out of 63 people are right-handed and they play on team sports. When you add those together, 3 plus 23, you just straight up add the numerators because you're talking about common denominator of 63. And we get our calculator out and we go, hey Siri, what's 26 divided by 63?
It's approximately 0.4126.
So you move the decimal 2 spaces because you're multiplying by 100, which means 41.3%. I rounded the 6, rounds the 2 up. Okay, suppose, wait, question. How did you know to apply the addition rule for probability? That the probability of A or B equals the probability of A plus the probability of B subtracted by the intersection of A and B, which there was none. So it's how we deal with the OR problem. OR in probability is add the probabilities separately. Only take away the overlap if there happens to be double covered probabilities, but in these two orange cells, they don't overlap. Their conditions don't overlap, so we just add them. Easy peasy. Suppose you randomly select a person from the survey. Determine each probability. The person is left-handed or participates in team sports. So because of the word or, we're going to add the probability of left-handed. We're going to add the probability of team sport, and we're going to take away the probability of both. So adding up left-handed, adding up team sport creates an overlap here. Now again, this is the just the frequency, not even relative. That was on this page. So I'm going to also, I guess, bring this one into consideration. Left-handed and team sport, there's overlap here. And so we want to be careful of that overlap to take that away from these two values being added together. So I have 39 out of 63 for team, 24 out of 63 for left. Referencing my materials. 24 out of 63 people are left-handed. 24 out of 63. 39 out of 63 are playing on a team sport, and then 13 out of 63 play on both. If you don't subtract off the 13, then if I were to count up individually, 3 plus 13 plus 8 plus 23 plus 3 plus 13 again, you got to take away one of them because 13 would be adding up twice. Add the fractions across the top, same denominator. And this is the addition rule for probability. So hey Siri, what's 24 plus 39 subtracted by 13?
Okay, I found this on the web.
Wow.
It's 24 plus.
I figured it would just calculate it. I'm having some issues here. We can also add up their individual percentages. So the probability of being left-handed is 38.1. We're going to add to that the probability of playing on a team, 61.9%. And then we're going to take away the probability of playing on a team and being left-handed, so the intersection, 20.6. Okay, if we hadn't done that, by the way, these two together probably would add up to like 100%. That means that everyone is left-handed or on a team. That's not true. There are people who are right-handed. There are people who don't play sports. So we can't get a 100% and think, drop the mic, I figured it out. No, you're missing the point that there's another percentage of people who are not on neither of those cases. Okay, so adding, subtracting, 79.4%. Hey Siri, what's 24 plus 39 subtract 13?
24 plus 39 minus 13 is 50.
Hey Siri, divide that number by 63.
Okay, I found this on the web.
Oh
for
my
dividing
good
it.
gosh, Siri doesn't like to divide by 63. I'm sorry, I'm subjecting this to you. I'm just going to do it. 50 divided by 63. 79.4, 79.4. Boom. The person does not play sports or is mixed-handed. You know what, honestly, you should try 8B based upon what we've talked about. I'm, of course, going to answer it, but pause the video, skip forward like a minute, and see if your work matches my work. Because if it does, I think you're getting it. And if it doesn't, go back and rewatch it. And think about the steps that I'm explaining as I go. So pause, do the math, come back and check. Okay, no sports. So no sports is this category. Or mixed-handed, this category. And there's overlap. So 22.2%. Mixed-handed, 9.5%. Not mixed or sports, so 3.2. There it is. 22.2% of people do not play sports from the survey of this collection of data. 9.5% of them are mixed-handed, ambidextrous, and there are 3.2% of them who are both in the category of no sports, mixed-handed. So we take that percentage away because it's added at least in both of these. Both of these percentages are increased by the 3.2%. So we got to take away one of them so the 3.2% is not double counted, leaving us with 28.5%. What does this tell you about the student population in Mr. Harris's class? Are they aligned with the general population of the planet or of the nation, or are they abnormal? That's what statistics and probability do, is they determine how likely it is that something would happen normally, randomly, or if there's an intentional application of something going on, like something in the water, people are more left-handed, therefore they play more sports, that sort of like thing. Okay, not trying to project anything, but that's what is considered after you look at a relative frequency table like this. How do the survey results compare with the estimate that between 70 and 90% of the world's population is right-handed? No. All right, the survey shows a lower percentage of right-handed people than the estimate for the world's population. I mean, right away you should have realized that those two numbers were way too close together. And if they're close together, that's more like 50-50. If the world population is boasting a 70 to 90% population of students who are people who are right-handed dominant, and Mr. Harris's class is showing only 52.4% of his students are right-handed dominant, well, then right there. That's it. Compare Harris's frequency table percentage to the world calculation. 52.4% is much lower than 70%. It's definitely much lower than 90%. So Mr. Harris's class is normal? Not bad, not in a bad way. Normal to the standard that between 70 and 90% of the world's population are right-handed. No, his class is not, which is totally fine. But that's what probability and statistics will do. How likely is it, and is that weird? We're going to consider some student responses in the next page, page 839, so stick around. Keep all of your Activity 2 material handouts with you as we answer the final page of Activity 2 and get ready to move forward, wrapping up this lesson. Thank you for watching, liking, commenting, and subscribing. I'll see you in the next episode.